thanks for coming. This talk was started, we were thinking about doing some experiments around performance in CSS, and searched the web with search engines, found very little. There's not a lot of research out there on this. So it occurred that maybe we should go to the guy with the secret knowledge. How does this stuff really work? We're poking at the black box, but we don't even know how it works. So I want to introduce David Barron. He's a software engineer at Mozilla, where he's worked since 1998. He's a member of the W3C CSS Standards Working Group, and he's here to present.
Thanks. So it'll be a little interesting, because right now I have the slides there, but I don't have them here. So I may get a little confused which way I'm moving the mouse at some point. But in any case, so what I'm going to talk about is really the so just, well, one little pointer is that if anyone can't see them, I also put the slides on the web, although they at dvaron.org/talks, but they sort of requires a relatively recent browser to look at, because I basically wrote them against Mozilla trunk using HTML and SVG, so it's a little fun. Anyway, essentially what I'm going to talk about is it's sort of a how browsers work from my perspective, which, you ask any engineer who works on web browsers how they work, and they work more in a different area, and they're going to be biased towards talking about that area of the browser rather than some of the other areas that they have less experience in. So I'm going to try and sort of give a how browsers work talk, but edited pretty heavily to focus on the parts that are relevant towards what authors can do to make web pages faster. But it's still fundamentally sort of, this is how a web browser goes from getting stuff on the wire to displaying stuff on the screen, but with a lot of other comments interjected in. So when I'm coming at this from the perspective of somebody who works at Mozilla. So I work on one web browser. I know a lot more about one than I know about the others. So a lot of the details that I'm going to get into, some of them are sort of pretty common across browsers, whereas some of the others vary more between browsers. And I'm not even necessarily sure in some cases which are which. And beyond that, a lot of these things vary between browser versions, in that when you're writing a web browser, you have a lot of compatibility requirements in terms of what you have to, basically, anything that you've shipped before that other browsers do too, you have to keep doing. And it's not necessarily that way with performance. If you're slow at something before, nobody's really going to complain if you find some way to speed it up. So we sort of have a lot more ability to change the performance characteristics of our layout engine than we do to change the output in terms of visual output or behavior or other characteristics. So an example of that would be like in Firefox 3, we made some pretty significant changes. Well, there were many significant changes between Firefox 2 and 3. But one of them that's relevant here is that the way we handle style changes changed drastically so that we would coalesce separate style changes and process them all at once, rather than processing them all separately, which could pretty significantly change performance characteristics of pages that were exercising that. But it doesn't break anyone. We have the ability to do that. So with that preface in mind, I want to just sort of dive in and talk about the data structures we have in web browsers and some of the things we do. So sort of one of the central data structures we have is the DOM tree or the content tree. We call it a bunch of different things. But basically, HTML, this bunch of tags, is a serialization of a tree structure. And most modern browsers actually turn that into an actual in-memory tree structure. In some older browsers, that actually wasn't the case. But these days, most browsers actually have a tree in memory. And when you use the DOM APIs that work on a tree, there's an underlying tree data structure that looks pretty much like you think it would look. So a simple HTML document has a bunch of HTML element nodes and a bunch of text nodes and so on. And the types of the nodes in this content tree are things like HTML elements, and then there are specific types of HTML elements. And they differ based on what DOM methods they have. You can also have an SVG DOM tree, or if you have something like the slides I'm using today, you can have a DOM tree that mixes both of them. But the thing about this tree structure is that the types of the nodes are related to the types of the elements. Then, in addition to that, and this starts to vary a little bit more between browsers, but I think it's still reasonably similar. We have a second tree structure that represents what we render for all of these elements. So we call it the frame tree, which is sort of odd, and I will tend to use that term just because it's the term I'm used to using. People will also call it the rendering tree. I'll probably use them interchangeably. The nodes in this tree all represent rectangles, essentially. But the more important difference is that the types of the objects in this tree aren't things like element types. They're things like CSS, the values of the CSS display property will mostly correspond to the types of nodes in this tree. So block or inline, or various table types or text nodes. In many cases, there's a one-to-one correspondence between the nodes in these trees, but in some cases, there isn't. For example, a node that has CSS DisplayNone wouldn't create any nodes in the rendering tree. So like you see in this slide, the head element doesn't have, there's no nodes in the rendering tree pointing to the head element because we make the head element display none, so there's just nothing generated there. Likewise, there are cases, especially when we break elements across lines or pages, where you'll have multiple rectangles representing a single element in the DOM. So with these two data structures, now I want to sort of walk through the process of what we do as we display a web page. So for a start, I'm actually going to start off to the left edge of this slide. But we start off, we're reading HTML. Things like parsing are mostly linear time in the length of the thing you're parsing. There's nothing all that complicated in terms of parsing that, at least that I'm interested in. Then again, it's sort of not as much the area that I work on, so I'm sure there are other people at Mozilla who could talk about performance aspects of parsing for quite a while. But there are actually in some cases, the process of parsing a document actually ends up not being linear time, not so much because of the algorithms, but because of the way it's done incrementally. And in particular, if one element has a very, very large number of children, you end up with some quadratic time algorithms showing up just because of the process of incrementally loading a document and incrementally adding those children. There's sort of a very small quadratic term because there's some operations, especially when you're dealing with laying out the document and displaying it, where you're going to walk over that child list as it incrementally grows every single time. Though, by and large, it's linear time. So the more interesting stuff about the process of loading a document is dealing with things like loading style sheets and loading scripts and loading images. Because when you're just sort of in this static version, and what I'm sort of going through now is the sort of the case of displaying an HTML document that's just static and doesn't change dynamically, which is sort of the basic case. And then I'm going to go back over again and talk about how we handle dynamic changes that are a lot more relevant to use of HTML in applications. But in any case, so loading images is sort of straightforward. When you're constructing the DOM tree, you hit a node that's an image, you kick off a network load that starts loading that image, and you just keep going. It's asynchronous. It's not giving you some huge penalty, although there's, of course, issues with we're limiting the number of HTTP connections to a given server. So there's some serialization against other resources that you might be loading. Scripts and style sheets are a little bit more interesting, because scripts have this model that I suspect a lot of you are familiar with, where what's in a script executes at that point. So right where the script is linked, you are executing that script. So you have to wait for the script to load, because the script could document.write a start tag and not an end tag. It could document.write all sorts of things. And the programming model used on the web is a synchronous model where where the script has to execute at the point it's loading. So when you're waiting for a script to load, you're often waiting for, you're essentially not even parsing the HTML to find other things to load. That was actually true until yesterday on Mozilla Trunk. We actually landed a patch yesterday that finally sort of speculatively parses the HTML after the script on the assumption that the script isn't going to do anything too serious, and starts initiating the network loads for things that it finds linked there. But even so, this is something that you have to be pretty careful with. Style sheets are sort of an in-between case, because the idea with style sheets is that they can have drastic effects on the rendering tree, but they have no effect on the DOM tree at all. So you really want to wait for style sheets to load before you construct the rendering tree, but you can keep building the DOM tree and potentially executing script even while they're loading. That said, the way that's happened has changed over time in Mozilla. The original way this was implemented is somebody said, oh, we need to do this. Why don't we just reuse the code for script? So in the old days, we actually did all the things that we do for script also for style sheets. That's changed such that we will now continue parsing the HTML, continue loading the page while we're waiting for a style sheet to load. But potentially, that means you're running scripts. And those scripts could potentially ask for the result for layout information, which means suddenly we need a rendering tree in order to give the script the information they asked for, which can potentially produce a problem that web developers hate so much that they've given it a name, which is flash of unstyled content. And since we've started doing this for style sheets in Mozilla, we've actually started having this type of problem in a few rare cases where a page asks for layout-related information. So this is all sort of the preface to building up this content tree. Once we have the content tree, we then have to go decide what types of objects to put in the rendering tree. And since the types of objects we put in the rendering tree depend on CSS styles, like the display property and some other properties, we actually have to compute the style for the element in order to construct the rendering tree. So the next thing I'm going to talk about is CSS Selector Matching, which is sort of fundamentally, it's from an algorithmic perspective, it sort of looks like it ought to be a bit of a performance hotspot, although it actually ends up not being that bad in most cases because of the way we optimize it. So the basic idea of CSS Selector Matching is that you have a set of elements in the content tree, and you have a set of CSS rules. And for each element, you're asking, does this selector, if this selector matches this element, then we'll use this rule. So fundamentally, you have a problem where you're running this algorithm for every pair of element and selector, which can add up to a lot. So the question is, first of all, how we optimize that, and second of all, what it is that can make that more or less expensive. So I actually want to briefly step through the unoptimized version of CSS Selector Matching, just so that it's clear how this works, because it says a few things about what types of CSS selectors can be faster or slower. So a CSS selector, the things over here on the right side of this slide are examples of pretty simple CSS selectors. The first one represents any div element. The second one represents any element with a class attribute that's item. The third is any element with an ID attribute that's sidebar. The fourth is any div element that has an ID attribute with ID sidebar. The fifth one represents any p element that is a descendant of a div element. So this is one of the things I wanted to talk about here, which is essentially the process of matching. So if we were trying to figure out which selectors match the body element, in the unoptimized case, you'd sort of look at this and say, no, it's not a div element. No, it doesn't have class item. No, it doesn't have ID sidebar. It doesn't really matter fundamentally which one you match here first. To match this one, the way pretty much all browsers do it is that CSS selectors match from right to left. So the first thing you look at when you're trying to match the selector is the part that's at the part to the right of the rightmost combinator, where the space is a combinator that represents is descendant of. The greater than sign represents is child of, and so on. So if you're trying to match the p, say this p element here, these rules, there's only one, there's no combinators in these. So you just look at the piece, the one simple selector, which is the unit between the combinators. And in these four cases, it doesn't match. In this case, when you try to find out if the p matches, the rightmost simple selector does match. So then you look at the combinator and say, well, we want to find an ancestor that's a div, so you look up and say, OK, this one matches. So it turns out that selector matches. Whereas with a selector like ul space p, if you're trying to see if it matches this p, you start at the p, it matches. Then you look for an ancestor. So you end up walking all the way up the tree looking for an ancestor to see if it matches. So if you're dealing with a deep document tree, you can potentially spend a lot of time even just on a single selector, never mind this problem of multiplying all the elements times all the selectors. So there are actually some selectors are even worse in that there's backtracking required. For example, this one here, body, you're looking for a p that is a descendant of a div that's the child of body. If you're trying to see if this p matches, what the browser will do is, well, it'll say that p matches the rightmost part. Then it'll find the div matches the next part. But this div doesn't match the next part. So since the body div relationship is a child relationship, you have to backtrack try to match this div against the middle part. That succeeds, but this fails to match body. Backtrack, match this against div, and finally you get a match the third time. So that's the unoptimized case. Now, the way we avoid the problem of having to match every element against every selector is that we hash the selectors into a bunch of buckets in advance to filter out the ones that we know aren't going to match. And all that filtering is done on the rightmost part of the selector. In other words, the part to the right of the last combinator. So essentially, we'll say that if a selector has an ID in that rightmost part of the selector, we'll stick it into a hash table for selectors that have an ID by its ID. If it has a class, we'll stick it into a hash table for selectors that have a class, unless it was already in the hash table for those with an ID. If it has a tag name, we'll stick it in a hash table by tag name. And otherwise, we'll just stick it in the list of all the selectors that we couldn't classify. So then when we want to find the selectors that match, say, this div here, what we'll do is go to our hash of selectors with IDs in them, pull out the entry for ID equals sidebar. There's no class on that div, so it doesn't matter. We'll then go to the hash for all the selectors for the hash of selectors by tag name and pull out the selectors that have div in that rightmost part. And we will then combine those lists and only run those selectors. So what this is saying is that in Mozilla, and I think this is also reasonably true in other browser engines, your selectors are going to cause much less of a performance problem if they're if the rightmost part of them is as specific as possible. Because then you won't even there won't even be any code at all to deal with testing them against all these other elements that probably are going to fail, but maybe not all that quickly in the algorithm. So in any case, so once we have the list of selectors that match, we have a set of we have a list of CSS rules that match. You take all the declarations, compute a property value for every element, and start constructing this rendering tree, which is, there aren't too many interesting performance characteristics of constructing the rendering tree in terms of the static case. It's pretty much you go build objects and pretty boring. Then once we have a rendering tree, we compute all the positions of those objects, which is like constructing the rendering tree. It's a recursive process in that, and so essentially the process of layout, which we sometimes call reflow at Mozilla, involves essentially assigning coordinates to the rectangle for all of these rendering objects. So traditional document layout algorithms tend to treat widths as inputs and heights as outputs. So it's essentially done as a recursive algorithm where a parent will have some width input. It'll compute its own width, tell its children to fit in that width, and they'll add up to some amount of height. And then you'll come back out to the parent. It'll finish, determine its own height, and pass that on back up to its own parent. Now, it's not completely true that widths are input and heights are output. There are cases where we use intrinsic widths of content, where essentially widths are output. But that's not too relevant here. Now, the code that does this is going to vary a lot by frame type. How it's optimized is going to vary a lot by frame type. So things like blocks and tables probably are optimized reasonably well. Unusual things might not be as careful about being efficient. Then once we've computed all these rectangles, we then come along and we want to actually display something. So we build a display list. for all the things that we have to display within a rectangle. And then we essentially paint that display list in back to front order using a 2D graphics API. Now, that's sort of, now in that painting process, there are some things that make it slower. For example, if you have opacity, which is group opacity, you have to composite things into an off-screen surface, or paint things into an off-screen surface and then composite that onto the rendering, and so on. But I don't want to go into that too much. Now, that's sort of the one pass through simplified version for the static case. Now, when you're building applications, you end up potentially dealing with more possibilities here. Sorry. So there's a lot of dynamic changes that when you're writing script, when you're writing, when you're writing script, that there's a bunch of different types of dynamic changes that can happen to cause changes in this whole pattern. So one of the simplest is sort of adding and removing elements from the DOM. Which is something you can do with DOM APIs. It's pretty common. Basically, in that case, you sort of run through this same pattern on the elements you added, the same static pattern in a pretty straightforward way. So it's not all that interesting in terms of unusual performance characteristics. However, there are a bunch of other types of changes that have different performance characteristics. So essentially, web browsers are, in some sense, CSS-centric, in that they've sort of used the design of CSS as sort of a central part of their architecture. So a lot of changes that affect layout are often sort of indirectly CSS changes that happen because something causes the computed style of CSS properties to change, which in turn causes the display to change. So examples of the simplest example of that change is simply changing the style attribute. So you change element.style on some element. You're pretty clearly changing the computed value, the computed style of an element. So there's sort of, I have this, there's sort of a bunch of different paths I drew here. So I'm sort of thinking about what types of content changes. If you change the computed style of an element, the style attribute of an element, you're going to change the computed style. There's no way around that. However, there are some other types of changes where you can avoid changing the computed style, but that sometimes change computed style. Like if you change an attribute, like the class attribute is pretty likely to affect computed style, but there are some attributes that are more or less likely to change the style. And we have some optimizations to detect whether or not they will, which I'll talk about in a second. Then there's sort of a third class of changes where the changes are actually not completely avoiding this system at all. One of the interesting ones there is scrolling, which scrolling is a pretty optimized process because it's something users do a lot. And it's something that graphics cards are reasonably good at doing in the common case, which is, in most cases, scrolling down a few pixels, you can simply tell the graphics card to move everything a few pixels up, and then you manually repaint the little slice at the bottom that appeared. So that not only avoids dealing with all of these systems except for painting, but it also avoids even repainting anything but the little region that changed at the bottom. Now, there are a bunch of cases where that's actually not the case, where we have to repaint everything. some of the obvious ones are if you use background detachment fixed or position fixed, which basically are a way of creating something that doesn't move when you scroll. Then if you're drawing something that's a composite of things that do move when you scroll and things that don't, you have to repaint the whole thing. You can't just move bits on the screen. There's actually a third case there that's sort of interesting, which is when you have overflow on an element. So the CSS overflow property lets you create something that's scrollable inside a document. If you have overflow on an element that has a transparent background and is on top of something that's not uniform, then we again have to repaint the whole thing when you scroll. And we've gotten better at detecting some of the optimization cases there. I think at this point we will actually detect, if you have something that is, if you're scrolling something that has a transparent background but is on top of something that has a uniform background, I think we'll still optimize that, but that's probably something that differs a good bit across browsers and versions as well. To move away from this, the scrolling is sort of an interesting side point because it's something that you can do programmatically through the DOM. You can change element.scrollTop and element.scrollLeft, which is often a much faster way of doing something that effects that people do by changing element.style.top and using absolute positioning or relative positioning to move things. Some of those effects can also be accomplished by scrolling something programmatically. And this could be something with overflow hidden, which still can be scrolled programmatically. And that's sort of a way to bypass this whole pipeline and just deal with the repainting. So then there's this third set of changes that sometimes cause recomputation of style and sometimes don't. These are things like changing attributes. And the classic case that needs to be pretty heavily optimized is what we call event states. Now, the event state that's important is in terms of optimization is the hover state. Because hover is a CSS selector that applies to whatever elements are under, basically the element that's underneath the mouse pointer and all of its ancestors. So in theory, what element matches that selector changes every time the user moves the mouse. So the optimization through which we avoid doing this recomputation of style is essentially geared towards optimizing that case so that we don't have to recompute style every time the user moves the mouse, which is that every time, so when when an element changes whether or not it's in the hover state, we essentially look at all of the CSS selectors that have hover somewhere in them. So not necessarily in the rightmost part, but we look at any CSS selector that has :hover in any part of the selector. If that selector matches, if that part of the selector all the way to the left end matches the element, then there might be some style change. Because you can have a selector like :hover space P that applies to any paragraph inside of an element that's currently in the hover state. So we need to check not only the rightmost part, but all the parts of the selector, which sort of yields a second guideline for fast CSS selectors, which is that there's any time you write something like hover in a selector or write an attribute selector based on the attribute chain, an attribute that changes a lot, it's also worthwhile to have that part of the selector be as specific as possible, even if it's not the rightmost part of the selector. So the reason this is so valuable to optimize is that at that point, we can check only one element. Whereas once we decide that we need to go through and recompute style for an element, that implies that we're also recomputing style for all of its descendants. both because of CSS inheritance, because a lot of properties are inherited, and because of it's pretty common to have selectors that move from that select based on ancestors. So the way of handling, so we sort of just handle that all in the same code. So it turns out that once we decide that we do need to do this restyling, we then coalesce as many restyles as possible. Now, essentially what this means in the normal case is that we post an event to the main event loop and say, when this event fires, we'll process all the restyles that have happened between the first one and when the event fires. However, the web has evolved with a synchronous programming model that doesn't let us quite do that. Because basically, the expectation of script authors and the expectation of all the pages that they've written that we have to be compatible with is that changes take effect immediately. So when we say that when we do things asynchronously, we can do that as an optimization. But then if a script asks for information that depends on the thing that we're planning to do later, we suddenly have to do that immediately to provide the information that the script wanted. And there's a lot of things, a lot of JavaScript, a lot of DOM APIs that actually require this information. So if you're looking at the computed style for an element, that requires that all the style be up to date. And it in fact requires that the layout be up to date in some cases. If you're asking for various properties like offset top or offset left, that requires that the layout be up to date, which in turn requires that the style be up to date. So there's a lot of things that cause us to flush our queue of all the things that we would like to coalesce. And that poses a potential danger to script authors because it's pretty easy to write a loop where you're making a change and then reading something that requires that change to be flushed. Whereas, for example, if this were split into two loops, you could read all the data that you needed and then make all the changes. You would then have all those changes coalesced, and it would be much faster to make all of them than if you forced them to all be flushed separately. So when we recompute the style for a bunch of elements, we then essentially compare the style for the old style data and the new style data. So we find out that, for example, the CSS display property changed. The display property affects what type of frames we constructed. So if the display property changes, we need to go construct frames and then go through the rest of the pipeline. If, say, the width property changes, that doesn't affect what type of rendering objects we construct, but it affects the layout, and so we need to go through the pipeline from here. It could also be that, say, the color property changed, at which point the color property doesn't affect the first two, so we can jump straight to the third. So when we handle all these things that change CSS properties, depending on the property, we'll do a different amount of work to handle that change. So then there's the question of how much work these different types of things take. So reconstructing frames for something, basically, if we reconstruct the frame for an element, we're also reconstructing the frames for all its descendants. That's just an invariant that we maintain. I don't know if other browsers do that or not. But it's not particularly, there's no interesting behavior regarding the depth of the tree, except for things like, except for a few odd cases where we have to go and reconstruct ancestors, because there are a few really strange cases, like when you have blocks inside of inline elements, where suddenly there's enough complicated fix-up that we need to go throw out a lot more in order to redo the fix-up from the top of the tree. Doing relayout or reflow is a little bit more interesting in that a relayout is always a recursive process running down from the top of the tree, because we have this algorithm where the widths are input and the heights are output. So if there's some change way down in the depth of the tree, it's possible that that change propagates out into different heights all the way back up to the top. So what we do, and potentially some other things that we need to update during layout, like the regions of overflow, which are sort of like a second rectangle. So when we do incremental reflow, there is this aspect that's a function of the depth of the tree. So this is a diagram that I stole from a presentation a colleague did 6 years ago. Essentially, we sort of we call these relayout methods all the way down the tree. And some of them aren't necessarily going to be all that efficient, but they, in turn, at least aren't going to relay out all of their children. They're going to just relay out the child on the path to get to what needs the layout. So the cost of doing relayout can be pretty heavily affected by the ancestors of that element. For example, if you have an element that's inside a floating element that's got a lot of other floating siblings, recovering state, the state we have to recover for floating elements is pretty substantial, because we need to rebuild state in order to know what areas we can wrap around and what areas not to wrap around. So the cost of a reflow can vary a lot, depending on what something is inside, not just depending on what it is that is being laid out again. So then the final step is repainting, where essentially what we're doing is we're invalidating regions, telling the operating system that a region's invalid. It'll then come back to us with a paint event telling us to repaint that region. So there's sort of this hierarchy of CSS properties in terms of which cause more damaging style changes than others. And this can introduce some trade-offs. For example, if you want to hide elements, there are actually multiple ways that you can hide an element. You can change it to be display none. And like I said earlier, making something display none means we're not going to construct any rendering objects for it. So if you change something to display none, we're going to destroy all the frames for it. And then if you change it back from display none to whatever it was before, we then have to rebuild all the frames, lay them out over again, and paint everything. If in turn you hide something with the visibility property, you don't incur any of those costs, because the visibility property doesn't affect the frame tree, it doesn't affect layout. But you have slightly higher costs in terms of what you're doing every time. In other words, the trade-off between display and visibility is essentially that with visibility, changes are cheaper, but the overall cost when it's not displayed is higher, because the visibility property, you still have the rendering objects, you still have to do all the layout, but then you just don't paint it. So I want to go back now and talk about some implications of this for things that you can, for ways to test. This is one of the things Lindsay asked me about when he asked me to give this talk, is that people were thinking about what types of things are useful in terms of testing performance of web pages. And some of that depends on what it is you want to test. But so one example is if you want to figure out essentially what the cost of building the frames and laying them out is for some particular piece of content, you could do something like the following. You could set the element, or maybe it's the body element, to be DisplayNone. Then you could get the offset top property of some random element in the tree, which will in turn flush all the style changes and flush the layout, so that you've essentially flushed the buffer of what's queued up. Then you get a timestamp. Then set the thing that you had set to DisplayNone back to its original value. Then again access offset top of some random element in order to flush everything. What that'll do is getting offset top will flush all the style changes. It'll recreate the frames and lay them out again. And then you can look at another timestamp to see essentially how heavy that chunk of markup is. Now, doing that within something that's dynamic could potentially throw in some confounding factors, because by forcing these flushes, you're also splitting up things that could potentially be coalesced within a real application. So likewise, something I talked about a little bit earlier is dealing with the costs of incremental layout. One of the things that might be interesting to test in terms of layout is how expensive some structure is in terms of its performance effects on relayout of what's inside of it. Because like I mentioned, the layout process depends on the depth of the tree. So you can do, again, similar things by checking an offset top, making some small change, and then seeing if different structures take shorter or longer amounts of time to handle a relayout. I'm sure there's lots and lots of other examples here, but those are just a small number. And hopefully I've given you some ideas here for other things that you can test. And I'm certainly open to questions about pretty much anything I talked about. Thanks. And I was told if you have questions, you should use the microphone.
Hello. Well, thanks for the great presentation. I do have a question. So a while back, you suggested using overflow hidden and changing scroll in order to move things around. Mm-hmm. But I found in the past when I've done that, it causes unrelated elements in the screen to kind of have stuff flash behind them. Do you know if there's a reason or a workaround for that, or?
I don't know. I'd be interested to see a test case for that. It's really not something that should happen. I don't know.
OK, I was just curious. Thank you.
Yeah.
Thanks for the great talk. I have a question about absolute positioning and what kind of optimizations you do to not reflow the rest of the tree when you move it around, for example.
So absolute positioning is sort of interesting in that absolute positioning is, the CSS specification defines this concept that it calls a containing block, where that's sort of for normal elements, it's the nearest block level ancestor. But for absolutely positioned elements, it's the nearest relatively positioned element or the viewport if there is no containing relative, the nearest positioned element, whether it's relatively or absolutely positioned, or the viewport. So for absolutely positioned, so when we build the frame tree, the absolutely positioned element is a child of its containing block. So for absolutely positioned elements that are positioned relative to the viewport, in other words, if their containing block is the viewport, then in our implementation, their parent is the viewport. So there's essentially no structure that you have to delve down through in order to get to them. But if an absolutely positioned element is inside a relatively positioned element that's inside some complicated structure, we actually are going to go all the way down through that structure to the relatively positioned element, and then jump from there straight to the absolutely positioned element.
Thanks.
Sure.
So you discussed the performance differences between hiding an object using DisplayNone versus visibility hidden. So that sounds sort of like an implementation detail, or is that actually, is that behavior somehow part of the standard?
So in terms of visibility, it sort of is part of the standard because visibility is something that can be overridden by descendants. So inside something that's visibility hidden, you could actually have something that's explicitly visibility visible, and then it suddenly appears again. So it is effectively part of the standard that elements with visibility hidden need to be laid out. As far as display, I mean, it's not strictly part of the standard, but if something's display none, you don't know what display value it would have if it weren't none, so you don't really know how, like, if you were to try to lay it out, you wouldn't know what display type to give it, because what type of rendering objects you construct and how you lay it out are a function of its display value.
So if you were building a 3-column layout for performance, do you pick tables or do you pick floats? It sounds from what you said, you distinguished table elements being very optimized from other things. So I wonder what your take is.
Tables and floats are both reasonably well optimized, although probably for different cases. I tend, when I'm trying to do a layout, I tend not to be worried so much about the performance aspects in terms of floats versus tables. I worry more about what can actually do the layout I want, because usually there's only one answer that I can come up with, at which point I just run with it. I think a lot of it depends on what, like, I don't think there's one answer I would give for that. Like, I think it depends on what exactly you're trying to do. What you want to be flexible, what you know widths of, and so on.
Question. Near the end, you were talking about if we were doing timing, we should start up a clock, do whatever it is we want, and then stop the clock. I found that any concept of timers or wall clocks is incredibly jittery with regards to browsers. Is there any other measure of work I can use in order to time it?
Not that I know of. So there's, I think there have been some improvements to the accuracy of things like date.now recently. It used to be very inaccurate on Windows, but I think that's fixed now. That is in Mozilla on Windows. My solution to timing things when the timers are inaccurate is always just do it more times.
Do you have performance benchmarks for layout and rendering to test that you've improved?
That we use on the, yeah, so we have a bunch of different performance benchmarks that we keep track of. Some of them are just page loading benchmarks, where we're essentially timing the load of a whole set of pages that were downloaded at some point and which we've, say, archived for that benchmark. We also have some other benchmarks that are testing particular things, a bunch of constructed tests to test DOM performance and graphics performance. Those are the... So we also have some benchmarks for application performance as well. But those are probably the key benchmarks that we're looking at all the time. There's also, people look at specific test cases as well, but not for tracking purposes.
Coming back to Lindsay's question about tables versus floats for horizontal layouts, what if you have deep nesting? Like if you want to create like a generally just a structure for laying things out horizontally, is deep nesting of tables generally more expensive than deep nesting of floats, or?
I can't think off the top of my head why one of them is going to be worse than another immediately. One factor is going to be that in some cases, tables require more intrinsic width computation. In that table cells have, there's sort of, any piece of content has two intrinsic widths. One is sort of, the simple way to think about it is using a paragraph as an example. If you lay out all the text in a paragraph on one line, that's the larger of the intrinsic widths. And then smaller intrinsic widths of the two intrinsic widths is the width of the longest word in the paragraph. And then you can sort of extrapolate those intrinsic widths outwards. So table cells have a rule that they will never go smaller than the smaller of those intrinsic widths, which means they always have to compute that one, even if you've assigned them a width. They will still check and compute it and make sure that they don't go below it, unless you're using fixed layout, in which case you don't have to deal with that. Now, some of that, with deep nesting of tables, depending on the browser, some browsers are going to respond pretty bad. Basically, whenever you have deep nesting of things that require intrinsic width computation, some browsers are going to respond pretty badly. In particular, Mozilla before, so Firefox 2 or earlier. And I suspect Internet Explorer also, because there's sort of two fundamentally different designs for how to do this intrinsic width calculation. And basically, Gecko recently changed. Between Firefox 2 and 3, Gecko changed from one to the other, so that now there's not as much of a penalty for dealing with deeply nested tables because we've essentially separated the two. But what we did back in Firefox 2 was intrinsic width computation was essentially also treated as a layout pass, where we would sort of say, do a layout at some arbitrary width, at infinite width, essentially. And so then the process of doing that would destroy the information that you had in the normal layout. So if you had a series of deeply nested things that all needed intrinsic width information, you could get into trouble essentially throwing away the layout to compute an intrinsic width and then having to rebuild it multiple times as you recurred down and up the tree in order to lay things out. So that's one reason you could get in trouble with deeply nested structures, although that should be much less of a problem in Firefox now and shouldn't be a problem in WebKit or Opera.
You had also mentioned dynamically altering an element that had a float element as an ancestor as being potentially expensive because more contextual information has to be recomputed?
Well, it's more any change where there's a bunch of floats somewhere along that path. Because essentially, when we lay out an element, we essentially so when we're doing layout on an element because one of its descendants needs to be laid out again, we still have to sort of look at each one of its children and say, so does this child need to be laid out? Does this child need to be laid out? And so on. And if that child is a float, then there's a bit of information that we deal with. So if something along the path has a lot of float children, that might be a problem. But some of these are some of those problems are things that only show up if you're, say, using single pixel divs to build a 1,000 by 1,000 image. People who do that tend to find all these performance problems in browsers that nobody else finds. So some of those things might only be things you hit with very large numbers of children. Anyway, thanks.